likely to work.
All right. What happens is...
You know, when a virus comes in to a cell, it just kind of explodes and just kind of releases naked genes, basically. If you're this bacteria, these things might take over your cells, so you've got to respond.
Most of the time, you have multiple weapons of defense.
If you've never seen this virus before, usually the first thing you do, says Eugene, is you send out these enzymes to attack the viruses. They're sort of like the ground troops, and they fight really hard.
But much of the time, they fail, and then no one will hear about you again.
They're not terribly sophisticated fighters, so very often the virus takes over, the bacteria dies.
But there is some non-zero probability that you actually survive the attack.
If you do, then what the bacteria will do is send in some new enzymes to basically clean up, to go out, find any stray viruses.
And then cut the enemy DNA into suitable small pieces.
And here, he says, is where you get to the storage part. Those enzymes will then take those little bits of virus and shove them into the bacteria's own DNA, right in those little spaces between the repeats.
Right there, and nowhere else.
So I use those spaces in my own DNA as a storage facility?
Yes, if you will, you use it as a memory device.
Because here's what happens. Next time that virus shows up, sprays its genes everywhere. Now you are prepared. And this is where the CRISPR story really gets going. Because instead of sending out the ground troops who are probably going to get their asses beat, now you can actually send out the big guns. And in fact, what the cell does is it will manufacture these special molecular assassins. And will give those assassins a copy of that little bit of virus DNA it has in storage. Basically saying, here, take this mugshot. If you see anything that matches this pattern, kill it.
And these attackers, do we know what one of them looks like?
Yep, so we know what the protein looks like. It actually looks, I would describe it a little bit like a clamshell.
Sort of imagine Pac-Man, but kind of misshapen and rough. And each one of these guys, what it has is a copy of that virus DNA. It's got the mugshot that it's kind of waving around. What then happens is that whenever the Pac-Man bumps into some virus DNA, it pulls apart the DNA, unzips it, reads it. If it's not the right one, it goes on. Nope. And if that RNA has the same sequence, then click, click, it just locks in.
And if that happens, then the DNA is trapped and molecular blades come out
and chop.
Cutting its head with a mighty blow.
Yeah.
Oh, so this is smart scissors.
So it's like, are you like the thing I got? Are you like the thing I got? You're like the thing I got. Snip, snip. All right, now we're gonna kill.
Oh,
yeah.
I see.
And it has to be exact. It has to be an exact match. When scientists first discovered this whole system, they were fascinated. They were working it out. They're like, oh, okay, then this happens, and this happens, this happens. Cool. But then, in walks the dude, Jennifer Doudna, with a crazy idea. Well, I don't know if it's crazy, but radical.
This could be an amazing technology.
This is a tool. This is a tool. Yeah.
Right.
This is a tool that we can use to cut DNA where we want to cut DNA. Her basic thought was, why don't we turn this defense into offense? Because these things, they seem to be really good at cutting, and yet they only seem to cut the things that are on their mugshot. So maybe I could just replace what's on their mugshot. So instead of them going after viruses, maybe they could go after a gene that causes Huntington's disease or hemophilia. For example, this is actually something that's been done. Say you got a mouse with something like hemophilia. This is a disease that's caused by one bad gene. So what you do is you take these little surgeons, you give them the mugshot for the bad gene, then you stick the surgeon with the new mugshot in a mouse, then you set it loose, and just like it's programmed to, it will find that gene and click, click, chop. The scissors will end up cutting exactly the gene you wanted to cut. So the bad gene's gone. Now the question is, how do you put in the good gene?
Right.
It turns out, actually, according to Jennifer Doudna, that that's actually not as hard as you would think.
Really?
Yeah, apparently what you do is just throw this new good gene kind of in the neighborhood of where the old gene used to be. Just in the general vicinity.
You don't have to get super precise. I mean, it turns out that, there are repair enzymes that are probably continually surveying and checking for breaks.
She says what'll happen is that inside the cell, these repair crews will come along, they'll see the break, they'll see the good gene just sitting there next to the break, they'll be like, all right, I'll just stick it in.
Put the pretty guy in this space.
Exactly.
So we take advantage of a natural repair pathway that cells have.
They trick both the cutters and the fixers.
Yeah, now we're not assassinating anymore. Now we're actually engineering. We've gone from killing to refashioning.
Although, haven't we been designing genes, doing a form of genetic engineering for, I don't know, like 30 years?
Yes, but not like this.
Genome editing technologies have been around for a long time, but none of them have been as powerful as CRISPR is.
That's Beth Shapiro from UC Santa Cruz. She was actually one of the biologists that I drunkenly talked to at that thing.
Was it a modern art museum? I can't even really remember.
I don't remember either.
Must have been quite an evening to have the setting be so vague.
Anyhow, here's how she put it to us. Back in the day, this was just like 2 years ago, you'd have these gene editor things, you would take one, put it in a cell.
And what happened before was you would give it some instructions about where to go, and it might go there, but it might go to somewhere that's kind of related to where that was.
So it's like, you just take a right at Staten Island, but it takes a left.
And not only would it take left Staten Island and not find there, but it would have cost you a fortune and taken up 6 months of your time to get that thing. And now, it's really easy.
You just give it that mugshot.
And it goes, I'm going to find that guy. Exactly.
So it seems to be pretty precise, and it's cheap. Like the old tools would set you back about $5,000 just to use them once. CRISPR, about $75. And here's the kicker, says Carl. It seems at the moment that you can take these things out of bacteria, stick them into almost any other creature, and it still works.
You can use the same CRISPR system on anything.
Can you, do it if corn is vulnerable
Do it
to
in
a
corn.
certain pest? You can do it in corn.
Do it in corn, do it in anything. I'm waiting for someone to say CRISPR doesn't work in species X, and I have not heard of that.
So basically what you have for the first time in science is this gene editing technology that is cheap, precise, and possibly universal. And Jennifer Doudna says the moment the full impact of that landed on her,
I literally had, the hairs on the back of my neck were standing up. Just processing the fact that this thing exists, and that you could actually program it to cut DNA, and just like this molecular scissors, and I can just program it and it cuts DNA wherever I want.
It is amazing, unless you think about it further, which we will do in just a moment. I feel a cloud coming in over the horizon. Just over there.
do you see?
I see
those
it's getting
clouds
sort
on
of
the horizon?
dark over there, but we'll be right back.
Hi, this is Tyler, and I'm calling from Portland, Oregon. Radiolab is supported by Constant Contact, whose email marketing automation tools and website builder are designed for small businesses and nonprofits. Learn more at ConstantContact.com.
Hi, this is Araceli Diaz calling from Lakewood, California. Radio